question we could ask is, why bother simplifying polynomials? It makes doing calculations with them easier when someone is looking at it or trying to read a polynomial. If it's in its simplest form, the essence of it, the information you need from it, will be much more evident to you. So when we're done and we have a polynomial expression from some calculation, it's considered required, or it's considered good practice to make it look as simple as possible, of course without changing the values a lot. So here's a rule. To simplify polynomials, you write them with the fewest terms possible, and you put them in order by alphabet and by degree. And I'll show you what that means very shortly. First, let's talk about combining like terms. And rather than using math to start with, I'm using happy faces, blue meanies, and who knows what that yellow thing is. But as I look at this, I'd like to combine like terms. So I need to look at it carefully and identify those terms that are similar. Those are certainly similar. Those are similar, and I have the yellow one just hanging there. So I could rewrite this in the fewest possible terms this way. I have 3 happy faces, 2 blue meanies, and 1 yellow who knows what. So I've combined all of those and written them in the fewest number of terms. Let's see how that works with math. We're going to look at simplifying expressions to ultimately get a monomial. How about 3z plus 4z? And going back to the very basics, we remember 3z means z plus z plus z, 3 of them. 4z is 4. We count them, and we find that we have 7z. So we just added those, and the reason we could add them was because the variable was exactly the same for both of those terms. We see that here. The variable is exactly the same. There is nothing else. So it's okay to add the coefficients in this case. We get 7z when we do. Here's another example. 8z minus 3z. We see that the variable expression is exactly the same for both of the terms, so that we can do the math just by subtracting and find that our result for this is 5z. Here's a rule. To simplify monomial expressions, combine the terms with the algebraic parts that are the same. We write down the same algebraic part and then add or subtract the coefficients. Let's look at something just a little bit more interesting. Here's another example. We have 6xy squared minus 5xy squared, and we have to carefully examine the variables to see if they are exactly the same. In this case, by observation, we see they are, and then we can do the math. 6 minus 5 is 1, so our result for this calculation would be 1xy squared. Now, let's look at this. This looks like it's something that we ought to be able to do. But in one case, I see that I have x to the first power, y to the second power. The second term has x to the second power, y to the first power. Since they are not exactly the same, I can't combine them, and I can't make a monomial out of them. I can't simplify them. I can't simplify them because they are different. So when I write this down, that's as good as I can do. I can't make it look any better than that. Here we have a trinomial. Let's see what we can do here. I have a squared b cubed in all 3 terms. So I have minus 1 plus 6 minus 12. I can treat the coefficients just like integers on the number line, with minus 1 for the first term, 6 for the second, minus 12 for the third. And when I work this out, I find that adding those three terms in that polynomial together gives me a monomial minus 7a squared b cubed. Let's look at another example. 10z minus 5z plus 4z minus 3z. Again, I see that I have only z's, and I can combine these pairwise just as I would do in a normal addition. 10 minus 5 is plus 5. Then I can add in the 4, 5 and 4, 9. Then take away the 3, which finally leaves me with a 6. So it's exactly like doing math on the number line as we've seen before. Let's look at yet another example. I have minus 8, a to the 5th, b to the 7th. Then I look at the other terms, and each one of those has an a to the 5th, b to the 7th. I can combine them pairwise. Minus 8 plus 2 gives me minus 6. Adding the 4 gives me a total final result of minus 2, a to the 5th, b to the 7th. And again, I have a monomial. Now that we've dealt with combining like terms to get monomials out of several expressions, let's put these things mixed up inside a polynomial and see what we need to do to spot them. So we're going now to talk about simplifying polynomials. And remember, when we talk about simplifying polynomials is to put them into the simplest possible form without changing their value, without changing their algebraic content. We want to do something that has the least number of symbols. For example, take a look at this. Perfectly valid mathematical expression, but we have a lot of parentheses and things to the 0 power. There's a y to the 1st power. How can we write this more simply? Like this. We don't need the plus on the y cubed. A plus minus 3 is the same as saying you just have a minus 3y squared, the same with the next term. And finally, y to the 0 isn't necessary, and for clarity, we don't really need the brackets. We can just say minus 8. So we haven't changed the value or the mathematical content. We've just made it look as straightforward as possible. Here's a rule. For writing polynomials in the simplest form, the first thing we need to do is combine like terms and write them with the fewest symbols possible. And as we'll see, we would like to write them in descending order of degree. So we need to look at the degree in each of the terms of a polynomial. When we've talked about the degree of a monomial, it's been clear it's been the sum of the exponents of all of the variables. But what about the degree of a polynomial? Because that has a number of separate terms in it. The degree of a polynomial is the degree of the highest term in the polynomial. Let's look at an example. Here is a polynomial, and we see right there that the first term has degree 4. Let's look at the degree of the other terms in that polynomial. X cubed y, if we add those, 3 plus 1 is 4. Xy squared, 1 plus 2 is 3. The term with just a y in it is degree 1. And the term with a 3, remember that could be y to the 0. So the 3 has degree 0. And we've put this one in descending order of degree. The degree of the highest term is equal to 4, so that is the degree of the polynomial. We would look at this polynomial and say that this is a polynomial of degree 4. When we write polynomials, we write them in descending order of degree, from the highest to the lowest degree, from the left to the right, just as you saw in that previous example. Let's look at this one. Here is a polynomial with the order all mixed up. Let's first identify the degree. X to the 1, y to the 1, that's degree 2. X to the 4, y to the 2 is degree 6. Y is degree 1, and y to the 5th is degree 5. We need to reorder this in descending order of degree. Let's draw some arrows and try to see if we can figure this out. The degree 6 term goes first, the degree 5th term second, and so forth. So I reorder them this way. There's degree 6, here's degree 5, degree 2, and finally degree 1. So I've ordered these correctly from left to right in descending order of degree. Let's look at another example. Let's spot the degree in each of the terms in this polynomial and then put them in descending order. That's degree 2 because of the a squared. That's degree 0 because there are no variables, or we could say there's an a to the 0 in there if we wanted to. The next one is degree 4 because we have a to the 1st and b cubed. Next one is pretty clear. There's an a to the 6th. And here is a to the 5th b of 5 plus 1 is 6. We have two terms of degree 6, one term of 4, one of 2, and one of 0. Let's reorder them this way, putting them in descending order of degree. Since the first two are of degree 6, by our rules at this point, we haven't specified which of those two should go first. It doesn't really matter. Some people put the simplest term first, other people put them strictly in alphabetical order. Take your pick, but the terms of degree 6 definitely have to go first in this case. We've come to another rule by looking at these examples. To simplify polynomials with terms of different degrees, here's what we do. We first combine the like terms so that we've compacted the polynomial as much as possible and made it as small as possible. Next, we identify the degree of each term, as you've seen me do. Then we arrange them in descending degrees from left to right. We arrange them in descending order from the highest to the lowest degree, from left to right. Let's look at another example. Again, remember that if you don't see an exponent on a variable, it implies that we understand that that exponent is 1. Let's spot the different variables that we might be able to combine. Here are 3 terms with degree 1, so we could combine those. Here are terms with degree 3. We're going to try to reorder these from the highest to the lowest degree, left to right. So I put the terms with the y cubes first on the left. Then I include the terms with y to the first power on the right. Those are degree 3. Those are degree 1. Now I can combine these. 7 plus 3 is 10. Minus 4 minus 5 is minus 9, plus 8, minus 1. So now I can combine these into one binomial, 10y cubed minus y. For expressions with more than one variable, it's a good idea, as I indicated before, to put these things in alphabetical order. So if you have 3 variables, a, b, and c, then it would be 12a squared b c cubed, for example, or 15 r to the 5th s squared t cubed. So we put those variables within the monomial in alphabetical order. It makes it easier to think about if we follow that procedure. Let's look at another example here. First, let's order or identify the degree of each of the terms in the monomial. There's one of degree 4, d squared e squared. That's degree 5, d cubed e squared, 3 plus 2. Here's one of degree 2, another of degree 4, and here's one of degree 2. Let's see what we can do about grouping the terms here. We have 3 d cubed e squared, that's degree 5. We have 2 of degree 4 and 2 of degree 2. Let's see if we can combine any of these terms. I notice the second term has d squared e squared in both variables, so that those two can be combined. They're both of degree 4. Let me reorder them now and write them in descending order. We have 3 d cubed e squared. There was nothing I could do with that. But here, for degree 4, I have a minus 4 plus 7, which gives me a plus 3. Now when I look at the 2 of degree 2, I see I have a dE and an e squared, so I can't combine them. I've done as much as I can in terms of arranging these in descending order. Let's review a little bit. Some problems require quite a few steps when you're working this. So you have to proceed systematically, particularly when things get a little complicated. Let's look at a situation which is a little more complex than what we've looked at before. The first thing we need to do, of course, is to identify the degree of each of the terms within that polynomial. We put ones where they're indicated, just to make sure we remember to add those in to get the correct degree of the polynomial. So the first term is degree 1. 2 plus 1 is 3. Q squared R1 is degree 3. There's q cubed, that's degree 3. There's another one of degree 3. 1 plus 2 is 3. 9q to the first power is degree 1. Minus 3q cubed is degree 3. And minus 5q squared R1 is also degree 3. So it would appear here I have 2 terms of degree 1 and 1, 2, 3, 4, 5 terms of degree 3. The next thing I need to do is rearrange these in descending order, which I've done here. All of the terms of degree 3 are on the left, and the 2 terms of degree 1 are on the right. The next thing I need to do is see if I can simplify this at all. So I need to identify like terms. Let's see if I can find any. There's a q squared r and another q squared r, so I have 3q squared r minus a 5q squared r. Are there any other like terms? Yes, here are 2 terms that are q cubed, so I have 2 other like terms there. And can you spot any other like terms in this expression? 2 more. There are some like terms there, 8q and 9q. Let's rewrite this with the like terms close to each other so that it's easy to do the math. Then I have 3q squared r minus 5q squared r plus q cubed minus 3q cubed. And then at the very end I have 8q plus 9q. Let's do the math with those. Again, in descending order, 3 minus 5 is minus 2. 1 minus 3 is minus 2. I bring down that term because there are no others like it, but I combine 8 and 9 to get 17q, and there is the final version of that very complex polynomial. Here's a really, really good one, and we'll have to do it very carefully. 175 mn minus 385 mn cubed. And I've chosen m and n deliberately here because they look alike. And that's going to force us to be very, very careful. The first thing we need to do is identify the degree of each of the terms in this complex expression. Just to make sure I don't miss anything, if there is a variable that doesn't expressly have an exponent, I put a 1 there. Now let's identify the expressions, and again, if I wanted to, I can, in the pure numbers, put in something to the 0th power to help me understand that if I have just a number, it's going to be a 0. So let's look at the degree. That's degree 2. There's a degree 4, 1 plus 3. Here's a degree 3, 2, 4. 3 plus 2 is degree 5. N cubed, that's degree 3. Something to the 0 or just a number is degree 0. Degree 3, n cubed. That will be degree 2, degree 4, and a degree 0. Next, we reorder these from the highest to the lowest degree in descending order. And just to be sure, as we do this, we're going to mark the terms. Here's where we're starting, and I'm just going to list all of the things of degree 5, 4, 3, 2 as I go down, and I'm going to cross them out as I go so that I know when I've got something and I won't count it twice. From highest to lowest degree, let's look at degree 5. I only have one term of degree 5, and I've written it down, and I've crossed off that term so I know I've dealt with it. What about degree 4? There are 3 terms of degree 4, and as I write them down here, I've marked those out. There are 3 terms of degree 3. I've written those down. 3 terms of degree 2. There is no term with a degree 1. Nothing with degree 1 in it. We're spared that at least. And finally, there are 2 terms, a 3 and an 8, of degree 0. The next step is to take each of these degree expressions one by one and see if we can simplify it, see if there are like terms that we can add together. Then when we're finished, we'll take that string that I have down there by degree and put them back together into the simplest form of the polynomial that I can possibly find. With the term of degree 5, since there's only one term, there's not much more I can do to it. There's only one term. Let's look at this, though. There are 3 terms here. Can I simplify anything here? I need to go to see if there is something I can identify. There is m to the first power n cubed in all 3 of those terms. So it looks like I can take the 3 terms and make a single term out of it by just adding. So I can do this stepwise. Minus 385 minus 7 is minus 392. Then I can add stepwise again and find that those 3 terms have been reduced to one term, minus 149 is the coefficient, m to the first power, n to the third power. I finished with that, and I put the simplest term there. We next go down and look at, is there anything I can do with degree 3? And look at the simplest possible case here. I see right away I have 2 terms with n cubed. Those are like terms. I can combine them. There's nothing I can do with the first term, so there I am for degree 3, and I'm done with that. Let's go on and look at degree 2. I have 3 terms there, and I see I have an mn in the first term, mn in the second term, and an mn in the third term. Can I combine those? Yes, I have 3 like terms, so I can do the math pairwise as I've done before and find that all of the terms of degree 2 condense into 1,357 mn, and I can put that back in my list. There are no degree 1 terms, and the degree 0 terms is 3 plus 8. I can combine that to 11 and replace that. We're almost done. We've identified the different degrees. We've added all of the like terms. So all we need to do now is write the polynomial out from highest to lowest degree. There it is. We have one more thing that we need to do to simplify this. We have the first powers still written explicitly. Just to make this a little simpler and a little easier for people to read, we can do this. Take the ones out wherever we found them, and now we're truly done.